to welcome everybody. Oh, Franklin, I got to admit him first.
I got him.
You got him? Okay.
Yep. I'll keep an eye on it.
Okay, appreciate that, Clayton. So I'd like to welcome everybody to the regular meeting of the RASC Edmonton Centre. The RASC Edmonton Centre respectfully acknowledges that we are residing on Treaty 6 territory, traditional lands of First Nations and Métis. I trust everybody had a smoky summer, managed to get past that and see some clear skies. And the Perseids, I hope everybody got a chance to see the Perseids this year, at least a couple of meteors. Yes. I know I was out with the grandchildren out here at the lake and set up a inflatable mattress and put them on it and put a comforter over them. And they said, well, what do we do? And I said, well, you just look up. And pretty soon there was a few oohs and ahs, and it was another memorable night. So I think we'll begin with, as we usually do, with the minutes of the last meeting, which was the minutes of the June 14th meeting. I don't know if Sucrete is here today or John.
I am here.
Oh, you are?
Yes.
Lovely.
My video isn't on.
Okay, and how are you feeling, first of all?
My stomach hurts.
Yeah.
Yeah. For anyone who doesn't know, I got my gallbladder removed last week, so I'm in pain.
Well, I hope you feel better, dear.
Thank you.
Yeah, we appreciate you making it today. The minutes of the June 14th meeting have been posted on the OneDrive. Are there any errors or omissions? Okay. Well, in that case,
if you want, I can also share share my screen if it's possible, because I do have minutes of the meetings pulled up.
Oh, that's okay, Sucrete. If they didn't see it, that's their problem. I've taken a look at them. They're good.
Okay, sounds good.
So maybe, Sucrete, I can get you to make a motion to approve the minutes.
Okay, I'd like to make a motion to approve the minutes of the meeting for June 14th, 2021. That has been posted on the OneDrive.
And do we have a seconder?
Abdur seconds.
Abdur seconds. All right. All in favor, members, you could say aye.
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 Any opposed? All right, the motion is carried. So now I'm going to ask Dr. Sharon Morsink, our past president, to introduce our guest speaker. So Sharon, over to you.
All right, thank you. Well, it gives me great pleasure, even though I'm slightly crying, that we have Mark Waldman here today. The reason why I'm crying is because we actually wanted him to come to the Northern Prairie Star Party. And of course, that turned out to be impossible. So we have yet again another online meeting, but I'm sure that this will be almost as good as being at Black Nugget Lake. Mark Waldman graduated with his MS degree in optics in 1977 from the University of Rochester and has over 40 years of experience being an optical engineer. He worked for quite a long time at Kodak, and he was involved as a test engineer for the optics for a number of really important space satellites, space telescopes. And so there was the Iconos satellite, which was basically an Earth observation. It's kind of like a spy satellite. I don't know if that's correct there, Mark. He also worked on NASA's Chandra X-ray Observatory, which is still running today and is responsible for some of the most amazing X-ray images that you see NASA showing. And of course, he's also been working on JWST, which is what he's going to be talking about today. And JWST is what we call the James Webb Space Telescope as well. We've been waiting impatiently for this thing to get launched. And so I'm hoping that Mark will be able to tell us a little bit more about how the launch is going to be going, and also about his work on the amazing optics for this telescope. So I think it's probably time for him to take it over.
Hi, thank you, Sharon. And let me just make sure that everybody can hear me okay.
You
Yep.
sound good. I think you
Okay,
just have to
very
share.
good. I'll share in just a moment here. So I'm very happy to be here. I would have much preferred to have been there at some point. I was excited to be asked to come and speak to you. The connection was made. I have a friend who's a friend of one of you, and I don't remember who the connection was through. My friend Kevin connected me with all of you, and so this has been a great program. I'm going to make a little adjustment over here. That will be better. So yes, I'm happy to talk about the James Webb Telescope, and let me do my technology thing here and get my slideshow up. I made a nice little list of all the things that I might be able to do. So let's see, that one, this one, do that, and that, do that, do that.
And Mark, I can tell you that we will be able to share a portion of the recording for you that is your presentation. I'm sure that's
That
not going
sounds
to be a
great.
problem.
That sounds great. That'll be just fine. So one of the things I need you to tell me is, are you seeing my presenter view or the full view on your screen?
We're seeing the full view.
That's great. That was one of the things that I wasn't quite sure how that was all going to work out when I started setting this up. So yes, we're going to have talk about the James Webb Space Telescope. And just a little bit about me. You did talk about my history a little bit. I spent a lot of years at Kodak on JWST. I actually need to make one more adjustment here, if I may. On JWST, I worked as on the test planning from 2005 to 2017 or so. Wait, what? I have to do one more adjustment. I had a monitor set up, and I'm going to turn that one off so that it does not have any risk of any feedback. That should be good. So we did a big test in 2017, the big optics test in Houston. I worked on that for a very long time, and since then I've been working as part of this commissioning team, and we'll talk quite a bit about that. Now what I'm going to do on the next slide is just to kind of give everybody a nice background and a good context. I have a couple of minute video, which is an introduction to to JWST. And so hopefully this will all work. I believe I have shared all of the right things from my system, and hopefully this works.
This is your telescope, an engineering marvel, an exploration powerhouse. Use it to look back in time and explore the first galaxies that formed after the Big Bang. To peer into atmospheres of planets orbiting the stars. It's your eyepiece to the uncharted, unknown, and unimagined. This is the largest, most complex, and challenging space telescope ever constructed. It will change our understanding of the universe and our place in it. The James Webb Space Telescope. Equipped with the largest primary mirror ever to be flown in space, at 6.5 meters, it's more than 6 times the size of the Hubble Space Telescope primary mirror. Webb's 4 cutting-edge infrared instruments and cameras operate at super cold temperatures. Temperatures colder than the surface of Pluto. Getting this cold is done with the help of the largest sun shield ever flown. A 5-layer, tennis court-sized sun shield that blocks heat from the sun, Earth and Moon. Webb will be the first telescope to detect light from the most distant galaxies in the universe. These first galaxies formed about 13.5 billion years ago, only 300 or so million years after the Big Bang. Webb carries advanced technologies to tackle some of the most fundamental questions about the universe. How did the first galaxies form and evolve? Are there chemical signatures of the building blocks of life on other worlds? Is our solar system unique? Launching such a large telescope into space is an incredible engineering challenge. Fully deployed, Webb is too large to fit inside any rocket fairing. Engineers designed it to be folded, like origami, to squeeze inside the European Space Agency's 5-meter diameter Ariane 5 rocket fairing. After launch, controllers on the ground deploy Webb remotely. Deployment is an intricate ballet. For nearly 3 weeks, controllers carefully unfold Webb. After this delicate dance, Webb's golden mirrors are precisely aligned using motors behind each hexagonal mirror segment, adjusting them to form one perfect mirror. Once the instruments are fully cooled, the exploration will begin. Webb is a technological challenge like no other, born of the efforts of thousands of people across the United States, Canada, and Europe. The James Webb Space Telescope is your telescope. Use it to explore, to challenge theories, to see sights yet unseen. It's yours to unfold the beauty and mystery in the universe and our place in it.
So that gives you a bit of a grounding in the telescope. This is one of the rooms at the Mission Operations Center in Baltimore, Maryland. And this is where I'll be sitting as part of the commissioning team. We're going to talk quite a bit about commissioning later, but this is what it looks like for the people who are monitoring and commanding the system. So here's what the topics are for tonight. We'll talk about what it is, the science themes, the primary mirror, deployment and the orbit, the science instruments, commissioning process, the observing plan. I have a spot for questions near the end. And then I have a little closing, couple of little things there. If you have questions, it would be best to hold them till the end. But if you have some things that are more like clarifications of something that I might have said that you'd like to have a clarification on, go ahead and pop those in the chat. Every once in a while on my layout here, I can take a look at the chat and I'll see if there's anything there. So that's the plan. So the JWST, as you saw, is a large infrared space telescope, 6.5 meters diameter primary mirror. Earlier, I think I was hearing about aperture fever. And so this is perhaps the ultimate, one of the almost ultimate aperture fevers that you can have. It is the scientific successor to HST, and it's an international program. And we'll talk a little bit more about what our European partners have been part of this, including Canada, which plays an important part. Dr. Mather is a Nobel laureate. He's our senior project scientist, and he got his Nobel Prize around the microwave background. And when I made this chart, the scheduled launch was October 31st. Many of you probably have seen that they have now announced an official launch date of December 18th. And so that is what we are planning to. That's the official new launch date coming up. So all of us who are part of the launch and commissioning team are very excited about that. And you also saw it's an Ariane 5 rocket from French Guiana. French Guiana is the European Space Agency's launch site where they launch all of their rockets. That is on the northeast coast of South America, just north of Brazil. So in August, it had completed the successful testing, and now we do know, of course, what the launch date is. So just to give you an idea of the size, here's a full-scale model that was built many years ago, and it actually has toured the country and I think the world as well. You kind of get an idea of how big it is from top to bottom. The top of the primary mirror to the bottom of the spacecraft, which is hard to see. It's below the whole sun shield. It's about 10 meters high. And I'm going to look at my notes here. The sun shield itself is about 14 by 21 meters. It's often spoken as being on the same size approximately as a tennis court that all has to unfold once it's in space. Here are the primary components of it. On the upper right-hand corner, you see the optical telescope element, which has all the optics in it, the 18 primary mirror segments, secondary mirror, and then there's a whole section after the primary mirror with another couple of mirrors, and that's where all the science instruments live. On the upper left, the science instrument module is where the science instruments live. We'll talk some more about those. There are some other details here, but below the sun shield is what's called the spacecraft bus. That is the place that has all the power and communications and computer systems and reaction wheels and all that kind of stuff. And then going back around to the sun shield as well. So those are the primary components of the telescope. And here's a 2-scale size comparison of the primary mirror. Area-wise, it's about 6 times more. And you kind of get a pretty good idea there. I think one of the most interesting numbers is what the payload mass is that JWST is just a little over half the mass of what Hubble is, even though it has an aperture so much larger, almost 6 times the primary mirror area. So, and even the primary mirror, which is larger, has a smaller mass. And it's because of all the technology advancements and the fact that these mirrors are made out of beryllium and it's a segmented system. And Hubble was a monolithic primary with a glass honeycomb structure. So here's a little comments about our international partners. NASA is doing the mission and the observatory, and I think one of the science instruments. The Canadian Space Agency is providing 2 of the science instruments, the Fine Guidance Sensor and something called the NIRISS, I wrote this one down, the Near Infrared Slitless Spectrometer. The European Space Agency is providing what's called the NIRSPEC, the Near Infrared Spectrometer, MIRI, the Mid-Infrared Imager, and they are doing the launch. The United Kingdom is essentially in charge of building MIRI, and the NIRSPEC is being built by Germany, and then the Ariane rocket comes from France. And down here you can see where the launch site is. So you kind of get an idea of where that's located. So now let's talk about what the science themes are. Back when the whole telescope was first conceived of, they had to figure out what were the goals of such a telescope. And there are 4 primary science themes for JWST. One of them is first light and reionization. Second one is looking at the assembly of galaxies, and then the birth of stars and protoplanetary systems, and planets and the origins of light. So if we go look at first light, it's the search for the first galaxies or the first luminous objects formed after the Big Bang. And so some of you may have seen this diagram before. Present time is all the way on the right-hand side, and going back to the left is back toward the Big Bang. And you can see on a nonlinear scale at the top how many years after the Big Bang the scale is. And HST is can look back here to about that 1 billion years after the Big Bang. JWST is going to try to look here into this reionization period, the formation of the first astronomical objects when first light was being generated as a result of the universe's process. So that is one of the goals, and we'll talk about this redshift in a minute. The second one, the assembly of galaxies, to determine how galaxies evolved from their formation until now. So we're really looking here at the history of the universe. That's the whole purpose of this. And on the left-hand side, these are some images from very distant and old galaxies. And on the right is an image of a closer and more modern galaxy. And so how did these evolve, being able to look at galaxies at different ages to see what that process is? The third one is to look at the formation of stars from when they first started and to the formation of planetary systems. And one of the most important parts about this being infrared is that the ability to see through the dust. The visible image has a lot of scattering from dust and gas, and the infrared image can be, will look through that and be able to see more deeply into these stellar nurseries. And planets of origins of life look at physical and chemical properties of planetary systems, including our own, and investigate the potential for life in those systems by looking for chemical elements that might have some signatures. And the two primary ways of doing that are to look for the absorption line spectrum of a planet passing in front of a star, doing a transit in front of a star, and using some of the spectrographic instruments that are on board and looking for spectral absorption. And of course, the transit method, looking for changes in the brightness of a star when a planet goes by. When I was looking this up, this is not my area of expertise. I'm more on the hardware side and the testing side, so I'm not an expert in the astronomy side. But looking to see that this transit method looks for a 0.01% to a 1% drop in what that light intensity was, that was an impressive number to me. So in order to do that, in order to do the science then drives what the design of the telescope is. So let's look at what the primary design features are of the JWST. So in order to see the faint stars in the galaxies, we need to have a large aperture. And because the aperture is so large, and as you saw in the video, it's so large it won't even fit in the rocket, it needs to be deployable. And it also has to be lightweight enough so that the rocket will launch it. And that led to the selection of all the mirrors in the OTE are beryllium mirrors. Beryllium is lightweight, it's stiff, it has a good stiffness to weight ratio, and it can be polished. So the mirrors are made out of beryllium. In order to see the earliest stars and galaxies and to see inside the dust clouds, we need an infrared telescope. And to see the earliest things, it's infrared because of the large redshift we'll be looking for, and to be able to, as I said, to mention inside the dust clouds. And that leads us to, since it's an infrared telescope, it needs to be very cold, cryogenic, so that the self-emission does not present problems. And in order to be cryogenic, as you'll see, there's the major sun shield and the orbit play together in order to make that happen. And the spectroscopic capabilities in the instruments are to support the exoplanet exploration. So I think that most of you who are astronomers understand why infrared and the concept of redshift. But the redshift is that light from an object that is receding, the light waves are stretched out and turned to a longer wavelength, so that the colors that we are seeing when we're observing them from here at our location are actually shifted to a longer wavelength in the red direction than what they were when they were emitted. And if something is approaching us, then that is a blue shift. The observations of the universe is that it's expanding, and so pretty much everything is moving away from everything else. So the objects that we are looking at are red shifted, and the further away ones are red shifted even more. I'm going to come back then to this diagram, and we'll just note that we're looking here at redshift +1 value of 10 or more to be moving to the left here. And here's the definition of what that redshift +1 is. And so if the Z +1 is around 10, then that means that light that was originally emitted in the visible wavelengths of about 0.5 micron are now in the 5 micron range. And so we need to be able to see the 5 micron wavelength and beyond. And so here's a chart that shows what the infrared sensitivity of Webb's instruments are. We haven't talked about the instruments specifically, but there's a list of them. And so you can see the wavelength from 1 to 5. All these instruments are equipped to be able to see up to this 5-micron wavelength, but the mid-infrared instrument is equipped to see very long wavelengths, almost up to 30 microns. So you can see that this is again part of the design of the optics as well as the instrumentation. And here's a little diagram of what the relative wavelength range is. Here's the Hubble range, which goes from near ultraviolet to the somewhat near infrared and covering the visible, and Webb goes all the way out here into the infrared. So I talked about the cryogenic nature of this, and that in order to do that, there are two primary ways that we keep the telescope cold. It operates at around 40 degrees Kelvin. I kind of noted that over here. And one of them is the orbit. So JWST is going to be at an orbit location called L2, the second Lagrange point. And because of the gravitational interaction of the Earth, or in any planet, but we're going to talk about the Earth here, with the sun, there are 5 different Lagrange points where there are special gravitational characteristics there that, that exist. L1 is on the inside, and there's actually a bunch of solar telescopes there, and L2 is out here on the outside. And so JWST will live out here at L2. It will actually orbit L2. We'll talk about that in a minute, because it's not a completely stable location, but that means that it and that the JWST, L2, and the Earth will all orbit the sun together, and it's about 1 million miles away. And so what you then do is make a sun shield, and you have the Earth and the sun all be on the hot side of the sun shield, essentially a big solar umbrella. You can see how hot it gets there. And then the optics are on the cold side, where the optics all run around 40 degrees Kelvin, including the science instruments, and you'll see that the MIRI even runs down to about 6 degrees Kelvin. Here's a little diagram of the orbit. The first one is not to scale. About here's the Earth, here's Hubble, here's the Moon, here's Webb at L2. I thought it was interesting to see the Hubble orbit to scale around the Earth. It's very close. It's only, what, about 250 miles up, or so 384,000 kilometers. To scale, here's the Earth, here's the Moon, and JWST is out here at about 1.5 million kilometers. So it's pretty far out there. Nothing is going to go visit it. So now this is a little this is going to be a very quick video showing the orbit, and I think there's some music in the background. I'm going to be quiet while it plays.
The Sun-Earth L2 point is where Webb's orbit around the Sun is synchronized with Earth's. At this point, 1 million miles from Earth, Webb is free from the thermal influences of the Earth and all eclipses. Additionally, the Sun, Earth, and Moon, the brightest objects in the sky, are hidden by the deployed sun shield, giving Webb a dark, cold, and stable environment to carry out its mission of discovery.
One interesting thing about that is that the orbit around L2 is it does only about 2 orbits per year around L2. So it's a very slow orbit. It's around 2 to 2.5 orbits per year. So I thought that was an interesting piece of that. So now let's talk about the sun shield, which is the other piece that keeps it cold. It's a 5-layer Kapton based, about a tennis court size. It folds all up, it deploys, and it's multiple layers, because any of the light that gets through the first, that is not reflected by the first layer, can get reflected by the second layer and essentially work its way out through and come out the edge. And similarly, the third layer, any of the heat energy can get reflected and come out the edge. 4th layer, 5th layer, so very little gets through. And here's a picture of what the sun shield looks like in one of its deployment demonstrations. Gives you a pretty good idea of what the size looks like. So that's the part about keeping it cold. The next portion is about the amazing primary mirror. This is a pretty cool picture just by itself. So somebody on a cherry picker here getting ready to do some inspections. Gives you an idea of these hexagonally shaped primary mirror segments that are 1.5 meters in diameter from point to point. There are 18 of them. They're doing an inspection here with the light. And you'll also see this black section around the edge is called the fringe. And because there's no structure to this telescope, this is in order to keep light peeking in around the edge of the primary mirror. There is an aperture stop later on in the system which matches the primary mirror and is a tiny bit bigger. So between the aperture stop that is later on in the system and this fringe, then that effectively blocks the light that might sneak in around the edge of the primary mirror. So, and you can see in the middle, this is the opening of the aft optics assembly. It's got a cover on it in this picture. And that after hitting the secondary, the light will go in there and bounce around a couple times before going to the instruments. And this structure on the front, that's the upside down V, is the secondary mirror struts. They're folded up now and they will unfold in space. Here's another, I talked about a lot of this stuff, hexagonal segments. It's beryllium lightweighted. It is coated with gold. And why is it coated with gold? For very high infrared reflectance. And it deploys in flight. You can see here that there's one wing that's folded back, kind of like an elephant ear. The other wing would be also folded for launch, secondary mirror folded up for launch. And so this upper part here fits into the fairing of the rocket. Here's a couple of pictures of one primary mirror segment. This shows you what the beryllium blank looks like before they worked on it, after it's hexagonal. They lightweight it by basically cutting this structure into the back. About 90% of the beryllium in the blank is actually cut away to make it lightweighted. And then it's coated and put on and then there's a primary mirror assembly that's built up, which has actuators on it that move it around for alignment. And then here's a cryo test of 6 primary mirror segment assemblies, one of which is coated and the other ones that were not yet coated in, I believe this might have been in Huntsville, Alabama at their test facility. And here's a little picture also for scale of removing the covers after the primary mirror was assembled, after the PMSA segments were put on the backplane. Then some lucky folks went out on these diving boards and removed the covers in order to then unveil the PMSA segments. And again, just seeing the aft optics assembly here in the middle. One of the very special things that makes this system work from an optical perspective is the ability to adjust the primary mirror segments. But initially, after their launch, the primary mirror segment assemblies is retracted onto pads that protect the delicate motors from the vibration during launch. And so then all of those are deployed. It's about a 1/2 inch or about 12 millimeters deployment. They get moved away from their stops. And when they're deployed, here's an exaggerated view of what those segments might look like because the deployment motors are not perfect. And there's a whole process that goes on that I'll actually mention briefly that has to take them from this deployed condition to this aligned condition. And the actuators, which are on the back of the PMSA, you'll see this is the back view of the PMSA. There are actuators here, and they provide adjustments literally on the scale of nanometers at cryo temperatures. This is one of the technology developments, was to develop these nanometer class actuators that can run at cryo. This just gives you a diagram of all the different PMSAs. The A segments actually have all the same figure. It's an aspheric primary mirror. The B segments have the same figure, and the C segments have all the same figure, but it is an aspheric primary mirror. It's very nearly parabolic. The kind of constant is 1 point and then about 4 or 5 zeros before there's any digits after that. So one could spend an entire hour, and there have been many papers written on this wavefront sensing and control process, which is how the PMSAs go from that random position after they're deployed to their final aligned position. And so I'm not going to spend a lot of time on it, but if you imagine each of these PMSAs being not aligned to the other one, then each one of them will generate an image of a star. So when they look at a single star, and they'll be using starlight to do this, there are 18 separate images. And so after doing a focus sweep to get some initial focus information, there's a process where they actually move, they take a picture, move one of the PMSAs, and take another picture in order to ultimately identify which dot goes with which PMSA. After that, they put them into this array configuration so that they now have them all identified. They go through some additional alignments, getting the secondary mirror aligned, and each of the PMSAs not only has position actuator, but it also has an actuator that changes its radius of curvature, essentially its focusing power. So those all have to be matched. And then they they tilt them in so that they stack them all together. And then there are some other phases that ultimately make sure that they are all phased in piston space and have the same radius of curvature until you finally get to the final alignment. And then from time to time, the wavefront maintenance happens. So this diagram is from this, this document. And so once the recording actually gets done, and it's not going to be published right away because NASA actually has to approve the fact that we're going to post it, but you can go and find that, or you can look up wavefront sensing and control. It's a pretty fascinating process. So moving on to deployment. It takes about 2 weeks from launch before it's fully deployed. You can see here it's about all the different pieces that get deployed. Here are the 2 weeks deployment. I think after about 2 or 3 days is when it passes the moon. I did not look that up, but that gives you an idea of the deployment portion. And the deployment is one of the most fascinating and nail-biting parts of this, because there's a lot of deployments that happen. And that's the first portion while it's on its way here to L2. So I think what's coming up next, I have some notes about a video that I'm going to show, which takes a couple of minutes. It is a time-lapse animated version of what portions of that deployment are going to be like. And if you want to look up online for longer video about the deployment, it is absolutely fascinating to see what has to happen on this. So I'm going to play this video. I believe there's no sound, but you can just see, and these don't happen, there's periods of time that happen in between each of these activities, but it's all condensed so you can see that. This is a trajectory burn. That's the antenna. And then they do another trajectory burn. And this is deploying, getting ready for the sun shield. And they do these pitches in order to control how the sun illuminates the system during these deployments. And you can see the telescope lifts up to give it some more space between the hot zone and the cold zone. There's some membrane covers, and if you look carefully, those deployed. And so here, this is pulling out the sun shield on one side. This pulls out the sun shield on the other side. And then there's cables that pull this up and make those 5 sections all separate from each other. This is in order to help, the momentum flap is to help control angular momentum. Some radiators. The star tracker, I think you can't see very much there. Here's some more radiators for thermal control. The thermal control is a very big deal. That is also for thermal control. That is infrared something. And here's the secondary mirror deployment, which is right at the very end. The wings come out to make the primary mirror. And then the other wing is going to deploy to make the rest of the primary mirror. And now you have a system. So I could watch that over and over again. I'm not going to, but that gives you an idea of the deployment. This gives you an idea of the size of the science instrument package. There are 5 instruments here: near spec, near infrared camera, mid infrared instrument, to do this. Fine guidance sensor and the nearest are all packaged in here into this very large structure. But how does that work in terms of imaging? This is a shared field instrument. So all of the instruments have access to the field at all times. And so the overall field is about 300 by 700 millimeters at the prime focus. And this is how the fields of the different instruments are laid out. The NIRCam has about a 2 arc-minute square over here and another 2 arc-minute square over here. And here's the near spec over here. And then the fine guidance sensor and the nearest and the MIRI. The MIRI is fascinating. It's got a bunch of other detectors over here. So whichever instrument is going to be imaging at the time, the telescope has to be pointed so that the object of interest lands in the correct portion of the field. These are coronagraphic locations up here that have coronagraphic masks in them. Could go on forever. So that gives you an idea of how that works. Since you guys are astronomers and are into detectors, I just wanted to just for one quick second, these detectors, of course, have been around for a long time. I think they were built at least 10 years ago. And so you can see that these are 2000 by 2004 megabyte arrays. And this is only a 2 megabyte array for the different instruments and how many total sensors there are on all the different instruments. And you get an idea of what that looks like here with the person holding it. All right, I'm going pretty fast here because there's a lot of information and I know it's coming at you in a hurry. And as I mentioned, so my participation is I worked on what was called the final optical test first. And that was most of my time on JWST. And what we did there was we put the telescope assembly with the science instruments into a giant test chamber at Johnson Space Center. And you get an idea here on the left, and I'm only going to talk about this here for this couple of minutes. Here's me down here standing in front of the door of this giant opening to the chamber. And this only shows about a third of the chamber height. It keeps going up and up and up. This was used to test the Apollo program. We pumped it down to hard vacuum. And there's a cryo shroud here that brought it down to operating temperatures, 30 to 40 Kelvin. And so we took a month to get cold. We did a month of testing, and it took a month to get warm before we could take it out. It was about a 3-month program. And then here I am sitting in front of computers for the commissioning team. We'll talk about commissioning coming up. So let me talk about commissioning now. The commissioning is what we do over the first 6 months after the launch. All the different subsystems need to be checked out and make sure that they're working correctly. I know there's a lot of words on this page, but basically, the first objective is to make sure that everything is working correctly. Each of the science instrument modes, and I'm trying to remember how many modes there are. Maybe a dozen or dozen and a half modes, different modes of operation will be approved to make sure that they're all ready. It takes 6 months. They've been planning this for decades to actually put the plan together. And what we've been doing for the past year or more is meeting at the Mission Control Center in Baltimore to rehearse the different portions of this program. So it's just like a show. We've been rehearsing, and then we come home, and then we go back for another week or 2-week rehearsal. And we've done about 5 or 6 of them so far in order to get the team all tuned up and make sure that everybody knows what their role is as we're going ahead. So this is so in terms of commissioning, and I'm not going to spend a lot of time on the details, but this gives you an idea of what that 6-month period looks like of the commissioning. That I will be there in Mission Control to help do this. The first portion is the deployment portion. There's a cooling and transition portion. Then there's this telescope commissioning, which essentially is this is when all those mirrors are aligned. The primary mirror is aligned, the secondary mirror is aligned. And you can see that this takes a pretty long time to do that process. It's one step at a time in order to execute all of those alignment steps. Once the telescope is aligned, and that's mostly done using the NIRCam. At the very end, we use multiple instruments to check across the whole field. And then at the end, we check out all the different modes, operating modes of all the SIs, the science instruments. And you can kind of see here, telescope aligned, when the near cam is ready, near spec is ready. You can see this very long link if you want to look up the commissioning process. There's some great information out there. This is all publicly available information. So that this whole presentation is built on that. One of the other important things is how it's cooled down. Because of the different thermal characteristics of all the different materials, it has to be cooled down in a very controlled way so as to avoid any stresses on the system that could potentially put too much stress on joints or materials. And so that's one portion. And so these are the cool down profiles of different portions of the telescope. This one up here is maintaining the cryocooler of the mirror instrument warm before we actually let it get cold in a hurry. And one of the other portions is this blue area is the water band, when water can condense on different parts of the telescope and freeze. And so they have to be very careful about working their way through here. And they do a bunch of checks for water beforehand and checks afterwards to make sure that there hasn't been any ice that's formed on any of the instruments. And you can see out here after 120 days, that is, or maybe even 100 days, that is how long it takes for the telescope to cool down, starting from launch. And a lot of the operations are all happening during this cool down. So I'm not going to spend any time in detail on this. I just wanted to point out that this is the first part of commissioning, and all the different pieces that go into this in terms of all of the planning for when all of the different pieces happen and the sequence. This is the transition period and all the different things that have to happen during this transition period. And then this is the telescope commissioning, when all of the optical alignments happen. Talked about segment image array and image stacking and things like that. So this is that very long period from 40 days to 121 days, 80 days long in order to do the alignment of the telescope. This is the some of the detail on the science instruments commissioning. So that kind of gives you an idea of all the details that go on there. So one more portion here. I'm going to pause to see if there's any chats that I need to pay attention to. It's been very quiet. Is that some people, so how do you get time on the telescope? You guys can pull your telescopes out middle of the night, but how do you get time on the telescope? There's an entire process that's been worked out very precise, very well, very meticulously with Hubble that will also be followed with JWST. There are proposals, the very beginning of this at the bottom, the general public and the science community can put in proposals for what things they want to look at. Then on the bottom, on the left-hand side here, the bottom left is a selection process. There's a committee that selects what the observations are that are going to be put into the plan. The top left is this whole implementation process where the observations get scheduled at the time when the telescope is looking at that portion of the sky. Then the data gets captured, and you can see this actually has a little image of both Hubble and JWST inside that circle. Then the data comes down to the Space Telescope Science Institute in Baltimore and gets processed and being available to the primary investigators and ultimately to the, I'll just say this goes into the archive, and then they're delivered on the bottom right to the primary investigators and ultimately shared among astronomers around the world. So that's the process. And there's a lot of words on this page also, but the things to talk about here are what is the observing plan for the very first year of the telescope. Cycle 1 is the observing plan. And there's 3 different types of observations. One is called early release. which is basically to demonstrate that everything works, and we get some PR value out of that. So about 500 hours of that. There's about 4,000 hours of guaranteed time observations, which are awarded to the teams, the scientists who worked on the system, who helped develop the key hardware and software. And then the rest of the proposals, about 6,000 hours based on the proposal process. Over 1,000 were received for the first year, 266 were selected. And if you add up all these hours, it's more than a year. And that's to make sure that there's no idle time if they need to take something out and put something else in. The scheduling, I'm going to just read this bullet because I want to say the scheduling is not trivial because of the way that the orientation of the JWST lives in its orbit. Only about 39% of the sky are observable at any time because the telescope can't tilt to allow any sunshine on it. But of course, as it makes a 1-year orbit around the sun, you can see the entire sky over that period. Just to give you an idea of the categories of what the observations are, you can take a look at this slide and see what the different categories are and how many programs there are in the early release observations. You can see in the guaranteed time observations what kinds of things are being looked at. This is now almost 10 times as many hours. And all these different categories have different numbers of programs in them. Extrasolar planets has a lot. Deep fields has a lot to be doing things like the Hubble Deep Field, looking at targeted galaxies. I'm leaving this up here for just a few moments so you can read through the different things that are on here. And then the general observations, this is 6,000 hours worth of observing, and you can see how many programs there are here for exoplanets and galaxies and all different kinds of astronomical and astrophysical topics of interest. So we're getting pretty close to the end. In my next slide, I'm going to pause for questions, which we'll do by chat, unless our host wants to do it differently, but I will be happy to look at the chat. This is a photograph of a launch in 2017. As I said, when I made these slides, it was for end of October. Now we are in the middle of December. So what we're going to do is I'm going to pause for questions, and then after I've answered as many questions as time allows, then I will rely on our host here to let me know when that's just about done. I will have just a minute or two of closing comments after that. So this slide now says questions, and I am going to look at the chat. Does the sun's solar cycle affect JWST? Wow, there's a question that I don't really know the answer to. Let's see, I'm going to guess that the primary effect is thermal. And so if the sun's thermal characteristics don't in a global condition change a whole lot, the answer is may or may not. I'm going to say no. All right, I'm going to scroll up here. So I get these are coming fast and furious now. Oh boy, okay, here, let's see. We get to the questions. I had a little conversation here at the very beginning. Let's see, what percentage of solar radiation is needed to power the array? Another question, I don't know a percentage. You kind of saw what the solar array size was when it unfolded. So a question quantitatively, I'm afraid I am failing the answering here of the questions. Let me go on here. Concerns about micrometeoroid impacts and allowances. So that's a great question, Dan. So the way that space things are designed in general, and JWST included, is that there's a lot of redundancy on board. It's the electronics and things like that that are the primary components that are susceptible. If electronic systems go down, then things don't run. So there are double and triple redundancies. I believe that the primary thing that the electronics are encased in boxes that shield them from radiation. If there's micrometeoroid impacts on the primary mirror, then it makes little holes, and that doesn't make a big difference. Little teeny weeny divots in a 6.5 meter optic. And so there's a whole reliability program also. There's a whole section of this program that computes what's the reliability and the probability of meeting the minimum 5-year success requirement. And then there's a goal of 10 years. I didn't talk about that. And so there is a chance that something could knock it out. A quick comment about the 10 years is, unlike Hubble, JWST does carry fuel on board. It's an asymmetric telescope, which means that the solar wind can impart angular momentum onto the system. And from time to time, that angular momentum has to be dumped or counteracted by using fuel to fire little jets. Otherwise, the amount of energy that the momentum wheels would have to carry is too much. Let's see. Thank you, Warren, to connect me with Kevin. Kevin is a good friend. And someday I would very much like to come and visit you during your star party. I would love to do that. Let's do that. Beryllium panels cast and then milled out. I think they're pressed. I'm not, again, too familiar with the actual process. I bet that there's papers on that. I think that probably casting them with the ribs in the first place would have been too complex when they did the trade-off studies and decided to do it that way. Is it essentially a Cassegrain delosite? It is a it's an anastigmat. It's basically a Cassegrain, but with a curved tertiary mirror. That's a Cassegrain primary, secondary, and then there is a curved tertiary mirror, and then there is a fold mirror after that that lives at the aperture stop, which is the place that I talked about they can do the aperture stopping. When imaging with 18 mirrors, could you not image 18 images on one mirror? The images stack at the focal plane. They don't image on top of this. I may not be understanding that. When imaging with 18 mirrors, could you not image 18 images on one mirror with the same result? Stack the images. I'm afraid I don't fully understand that one. Hubble, let's see. Is there any hope of fixing problems of JWST? I'm not aware of any programs to plan to go and fix it, so no. The question, next one, is any collaboration with other telescopes? There are other telescopes there's Chandra and there's Hubble and there's other ones, and I am going to imagine that there will be multiple observations at different wavelengths made nearly simultaneously. I don't actually know this for sure, but I believe this will be what they'll do in order to be collaborative imaging between JWST and other spaceborne scopes. I don't know if they'll do them with ground-based scopes, but if you can get that wide wavelength range from different telescopes on a particular object, that would be that's a lot of great information. Let's see here, what else do we have? Let's see, those are all the ones that I see on my chat. I am going to pause for a moment to see if that is it or if I missed any. Let's see. Oh, those are great questions, by the way. Chris, did you want to say anything else about your question about 18 images, or did I? If I nailed it, then that's. If I, explained it well enough, that's fine. So I think what I will do is I will proceed and just finish this off. Close my chat here. So in terms of resources, jwst.nasa.gov, I bet some of you have found that already. It is an absolutely amazing and well put together website. If you go to that site, this is what it looked like when I put the slide together, and I think it's pretty close still. If you click on Navigate Site, you'll see all these different things. So the animations and the videos come out of the multimedia section. There's images of the hardware. There's all kinds of things. I opened up the multimedia on purpose because I thought that, there's all kinds of great stuff. But about the Webb and about the science and about the observatory and about the science instruments, there is just a wealth of information about JWST pre-launch that you can learn about. And here's my email. If you would like to ask me a question, I'm at optics@markwaldman.com. I would be very pleased to answer a question for you. I am not doing any more professional consulting, as they say, but questions about the telescope and other things like that, it's great fun for me to answer things and to let people know what's going on. So the last slide here is a little video, just to give you a flyby of JWST as it is heading to its final location. We like to say that the James Webb Space Telescope truly is out of this world. So we'll let us do the full flyby of this animation. Of course, there won't be any way to see it out there. There's no drone going with it, but this is just a really fun flyby. There we go. I am going to stop sharing and turn this back over to our host and see if there's any. Let's see, there were a couple of other questions I think that came up here. I miss any. Does the moon's gravity provide any advantage? Not sure. Again, the trajectory planning and that part is not not. But I know that there are launch periods that are go and launch periods that are not go, having to do with the moon and eclipses and things like that. So I don't know if it's gravity, but it does probably have effects of wanting to pay attention to when the moon is close by to where it's going to be. There we go.
Okay, well, I think let's all thank Mark for a wonderful talk. We've all learned a lot. I think we could probably unmute and clap. And
Ooh, thank you.
Yay! Do you want me to address any other questions, or if we need to tie it up here, Sharon, I'm happy to do that.
well, it looks like there's a couple more questions.
The lifespan of the array, I'm going to tell you the lifespan of the telescope is 5 years. The spec is 5 years guaranteed, with a goal of 10 or more, based primarily on the fuel on board. The array should last longer. What have I learned about James Webb? James Webb was the administrator of NASA during the moon program, and so was involved in helping to launch a lot of the science programs, as well as the manned program. I know that in some of the chat and areas around the telescope, there's some more conversation about James Webb out there, but that's the part that I know pretty much about. So, Sharon, I think, was that you who was moderating? I couldn't quite tell.
Okay, thanks so much again. This is really wonderful, and maybe in my dreams you'll get to visit us sometime in a couple of years, and you'll be able to tell us more about all the cool things that JWST has done.
In my dreams too, I would love to come and be there and not only meet you and be at the star party, but also that part of the world is on my list. So once all the travel stuff gets sorted out, then that is something we'll be doing.
Okay, great. Well, let's thank him again, and I think we turn this over to Tom now.
Well, thank you very much. Well done, Mark. Really appreciate it. It was very interesting, very thorough, and well presented. So on behalf of everybody here, thank you very much. It was just great.
Well, it was my pleasure, and talking about this is one of my push to talk buttons, as you see. It's great fun to educate about this. Thanks again.
Awesome. And you're welcome to stick around. We're going to move on now to, we're going to sit back and enjoy news from space. It is being presented by our past president, Jeff Robertson, and there is a little bit on the James Webb at the end of this, Mark. So, Jeff, why don't you take it away?
Oh, okay. So this is 3 months of stuff I've gathered. Normally I keep this thing under 15 minutes, but with 3 months, it's a little bit longer, and I've left out a lot of news just to make, so it wouldn't go way over. So anyway, I'll share my screen, share the sound. There's
On June 17th, China prepares to launch its first crew to the new Tianhe space station. The 3-man crew rides atop a Long March 2F booster in their Shenzhou 12 spacecraft. The Shenzhou 12 is soon in orbit and extends its solar panels as it makes its way to the space station. A few hours later, it catches up to Tianhe and maneuvers in for a safe docking. Successfully docked, the hatch is open, and the world's newest orbiting outpost welcomes its first visitors. The 3 crew members seem to enjoy the weightlessness environment and the roominess of the station. But there's work to be done. 2 of the crew perform an EVA to install equipment on the exterior of the station. The station's remote arm is also used.
这是我们的实验机柜，叫做人系统柜。
But there's also time to explain to the folks at home some of the experiments they do on board Tianhe.
通过采集我们的脑电信号，可以知道我们工作时大脑的功能状态。
Russia prepares the new Nyoka multifunction module at the Baikonur Space Center for launch to the International Space Station. The module is enclosed in its launch fairing and moved to be mated to a Proton rocket. From there, it's transported to the launch pad. There, it is erected and prepared for launch. The Nyoka module has a variety of scientific experiments to be carried out, plus a new airlock and docking port. On July 21st, it is launched for the International Space Station. It will arrive 9 days later. The Nyoka module will be mated to the station on the Zvezda module, currently occupied by the Pirs module. The Pirs module functions as the Russian airlock and docking port, and at the time of the launch of Nyoka, had a Progress cargo ship docked there. The Pirs module, with Progress still attached, is disconnected from the station. The assembly pulls away from the station, where it will burn up in the atmosphere when the Progress deorbits.
The Pirs docking compartment is free from the International Space Station that had been its home for the past 20 years.
205 for the primary program, command 40 not required.
On July 29th, Nyoka closes in on the International Space Station.
Indicators not.
There's our first view of the multi-purpose laboratory module from external cameras on the International Space Station.
Now proceeding to translational hand controller test. Copy. Up.
Cameras on the ISS and on the module itself monitor the approach. Moving at a fraction of a meter per second toward the docking port, Nyoka makes multiple control jet firings during the final approach. Docking is accomplished, and all seems well. But a few hours later, the new module's control jets begin firing on their own. The station spins out of its normal orientation, alarming the crew. A software problem is responsible. Soon, control is re-established. In other ISS news, astronauts conduct multiple EVAs to add new solar panels to bolster power supplies on the station. The panels were carried on a Dragon cargo craft that arrived in June. After years of development, delay, and a fatal crash, Virgin Galactic's suborbital spaceplane Unity is finally ready to carry passengers to the edge of space. The spaceplane, slung underneath its mothership Eve, will be carried to 50,000 feet, where it will be dropped. From there, it will use its rocket engine to climb to the edge of space. Putting his money where his mouth is, company founder Sir Richard Branson will be one of the 4 passengers and 2 pilots making the flight.
Seconds.
5, 3, 2, 1, release.
The space plane is released and ignites its engine, which burns a hydroxide-terminated polybutadiene compound. The engine burns for 63 seconds and accelerates the craft to Mach 3. Following engine burnout, the craft continues to climb to 86.1 kilometers, and Sir Richard Branson has this to say.
So all you kids down there, I was once a child with a dream, looking up to the stars. Now I'm an adult in a spaceship with lots of other wonderful adults looking down to our beautiful, beautiful Earth. To the next generation of dreamers, if we can do this, just imagine what you can do.
For a few minutes, the passengers frolic in the microgravity environment and gaze down upon our world.
Woo!
But a suborbital flight is fleeting, and the space plane is soon on its final approach for landing. Gliding down to the runway, the flight is over, 90 minutes after they left the ground and 12 minutes after being released from the mothership.
Congratulations. Thank you so much.
Passengers are ecstatic as they emerge from the craft. Branson has reason to celebrate. As the flight exceeded 50 miles by American standards, it's recorded as an official space flight. For $450,000, you can ride with Virgin Galactic, but Sir Richard does have some competition. Amazon founder Jeff Bezos has his own suborbital ticket to space with his Blue Origin New Shepard rocket. He's going to be on board for its first crewed flight. Joining him on the flight will be his brother Mark Bezos, pioneering aviator 82-year-old Wally Funk, and this guy. Unlike the Virgin Galactic spaceplane, New Shepard, named after astronaut Alan Shepard, flies a ballistic trajectory and has no pilot. The craft is fully automated.
4, command engine start. 2, 1. Ignition. We have liftoff. Shepard cleared down.
The rocket lifts off. The engine, which burns liquid oxygen and liquid hydrogen, burns for 141 seconds, accelerating the rocket to 3,500 kilometers an hour.
A beautiful shot.
After engine cutoff, the capsule separates and continues in a ballistic arc to 107.5 kilometers above the Earth.
Unreal.
The internationally recognized FAI boundary for space is 100 kilometers. In the few minutes of microgravity, the passengers take in views of the Earth and frolic in the strange zero-G environment.
And there we go. Our astronauts have passed the Kármán line at about 328,000 feet, continuing their ascent. You see the two vehicles there. When the speed hits zero, you know that they've hit apogee, their maximum altitude, and you hear they're having quite an experience.
twin sonic booms announce the return of the booster rocket. It fires its engine once more.
The sonic boom.
It makes a perfect landing, ready to be reused, and once again carry passengers to the edge of space.
And booster touchdown, welcome back, New Shepard. A beautiful rocket that provided a beautiful flight to space.
First up, your booster has landed. Stand by drogues. Stand by drogues.
The separated capsule descends on its own under parachutes. Like the Russian Soyuz, New Shepard fires rockets just above the ground to cushion the landing.
Just sitting in a chair.
And touchdown. Welcome back, New Shepard's first human crew. What a flight.
Welcome back to Earth, first step. Congratulations to all of you.
Ah, what a day, what a day.
After a flight of less than 11 minutes, the hatch opens and the 4 passengers emerge to a joyous welcome. If you have $400,000 handy, you can be the next passengers aboard Blue Origin's New Shepard rocket.
Hey kids, want the excitement of Blue Origin's New Shepard rocket but don't have several $100,000 to spare? Estes, the largest maker of model rockets, has just the thing. This scale model of New Shepard comes ready to fly, launch pad and engine sold separately. Watch it soar hundreds of feet and come back on its own parachute. Even the capsule separates and has its own parachute. Be like Jeff Bezos. Estes New Shepard rocket. Cowboy hat not included.
Since landing on Mars on May 15th, China's Tianwen lander and Zhurong rover have continued to study the Martian environment. A remote camera placed by the rover took this group picture of the lander and rover together before the rover went off to explore. Zhurong sampled the soil, drilled into the surface, and ventured over 1 kilometer during the 90-day primary mission. One site it visited was the aeroshell and parachute that carried the rover to the surface. As the Zhurong rover is still in very good shape, its mission has been extended. Meanwhile, NASA's Perseverance rover, which landed in February, continues its work in Jezero Crater, making its way to a dried-up river delta. One of its tasks is to collect soil samples that will be picked up by a future craft and returned to Earth. The samples will be placed in a metal tube and dropped on the Martian surface. The first attempt to do this resulted in an empty sample tube. Engineers are working on a solution and will try again in September to collect a sample. Accompanying Perseverance is the Ingenuity helicopter. The plucky little craft has exceeded all expectations and has, to the end of August, flown over a kilometer above the Martian surface. On its 12th flight, it spied the Perseverance rover from the air. Let us not forget about the Curiosity rover, which celebrated its 9th year on the Martian surface. Happy birthday, Curiosity! Record heat waves in Western North America. Unprecedented floods in Central Europe and China. entire communities destroyed by wildfires, crop failures on the prairies. Our bill is coming due after decades of pumping greenhouse gases into the atmosphere. At a June 9th committee meeting in Washington, D.C., Texas Republican Louis Gohmert asked if a celestial solution to climate change was possible.
And so, is there anything that the National Forest Service or BLM can do to change the course of the moon's orbit or the Earth's orbit around the sun? Obviously, that would have profound effects on our climate.
Mocked as being the dumbest person in Congress, Gohmert tweeted that BLM is the Bureau of Land Management and not, as he thought the mocking was about, Black Lives Matter. Moving the moon, I wonder. The private launch company Astra attempts to launch a U.S. military payload from the Kodiak Island, Alaska Pacific rocket range. Things go sideways quickly, both figuratively and literally, when one of the 5 engines on the first stage shuts down immediately after liftoff. With a thrust-to-weight ratio of 1, the rocket tracks horizontally until it burns enough fuel to reduce its weight so that it can begin climbing. The guidance software manages to keep the rocket pointed upward during this time.
Our next milestone is MECO, or main
With the
engine
flight
shut-off.
profile in tatters due to the anomaly, the rocket is too low when the stage's fuel runs out, and it tumbles out of control into the Pacific Ocean.
Terminate send.
Oh well, back to the drawing board. After an almost 2-year delay, Boeing's Starliner rolls out to the pad for its second test flight to the International Space Station. Anticipation is high for a launch in early August. However, valves are stuck closed in the spacecraft. The Atlas V, topped with Starliner, is rolled back. The Starliner is removed and sent back to the hangar. The next launch attempt won't come until 2022. The James Webb Space Telescope is at last ready to be launched. Like a city bridge project, it was overdue and over budget, but it is now complete. In August, it was packaged up, ready to be sent to French Guiana, where it will be launched on a European Space Agency Ariane 5 rocket. The telescope has a 6.5-meter mirror made up of 18 segments. Its launch date is December 18th, 2021. Leaving the Earth, it will journey 1.5 million kilometers to the Grange Point 2, where it will conduct its observations.
And
Jeff,
that's it.
That was awesome.
Oh, glad you liked it anyway. I hope
Well
other
done.
people did too.
Well done. So we're going to continue. We're going to make Abdur a co-host, and we're going to carry on with Astro Imaging Corner. Over to you, Abdur.
Thanks, Tom. Just going to share my screen here. Okay, can everybody see that?
Yes, we can.
Yep, I can see it.
Okay, perfect. Thank you. Just make that full screen. Okay, so welcome to Astro Imaging Corner number 112, everyone. So I received quite a few images for this month's Astro Imaging Corner, since it's been a little while since the last one. So for anyone who submitted, more than 3 or 4 images, I have saved the rest for next time's Astro Imaging Corner. So I will show those at November's Astro Imaging Corner. No, October's. I forgot my months. Okay, so our first image today is from Tom Wu, and that is the Sol Nebula. And Tom took this one at I believe it was at Pigeon Lake. Yeah, Pigeon Lake on August 23rd and 24th, and then on September 2nd and 3rd. And Tom used hydrogen alpha, oxygen, and S2 filters for this one. And the individual bin exposures were 5 or 6 minutes. And this was a total exposure time of 5 hours and 55 minutes. And Tom was using a 80 millimeter Orion triplet refractor at f6 and his QSI 683 CCD camera. And the images were stacked in Deep Sky Stacker and then cropped and processed in the Hubble palette using star tools. So great job, Tom. Yep, just gonna make sure I'm not missing anything in the chat over here. No, it looks like we're fine. Our next image here is from Rick Bram. This is the sun in hydrogen alpha. Rick was using a 100 millimeter Lunt modular telescope with a single etalon and a TeleVue 2.5x power mate. And the camera was the Canon EOS RA that Rick was shooting in RAW mode. And this is actually just one single image. This is not a stacked image. So that's a phenomenal amount of detail in there, especially for a single image. So great job as always, Rick. And this was the major sunspot region going on at the time. And on the solar surface, you can see some prominences around here as well. And this next image is also the sun in hydrogen alpha. And again, this was a single image, not a stacked image. And you can see some massive prominences coming off the solar surface and multiple sunspot regions visible over here. And the next image here is from Ray Weens. This is the aurora that Rick had captured at Blackfoot. And this was taken using a Sony a7R II full frame camera and a Sony 24 millimeter 1.4 lens. So very, very nice colors, Ray. And this is from the same night as well, after some clouds moved into view. And this is the Milky Way with the, I believe that's the Athabasca Glacier over there. Actually, this one was at Ape Lake, BC. And this was a 30-second exposure to ISO 2000 using a Sony full-frame a7R II camera and the Sony 24 millimeter f1.4 lens. And this was tracked using a Skywatcher star tracker and processed in Lightroom. So great job, Ray. And this is Messier 20, the Trifid Nebula. And this was a combination of 8 300-second exposures taken with a 132 millimeter William Optics refractor and the full frame QHY 367 camera. And this was taken in SharpCap and processed in Lightroom. And our next image is from Yusuf Hussain. This is the Andromeda Galaxy. It's phenomenal results with the hydrogen alpha 2 regions very, very well visible. And this was Yusuf's first attempt at combining data from LRGB, hydrogen alpha, O2, and S2 filters into a single photo. So I'd say you got some amazing results there. And this was taken at Black Nugget Lake on September 9th. And the equipment used was a Skywatcher Spirit 120 ED refractor. And Yusuf was using an EQ6R Pro mount. And the imaging camera was the ASI 6200 monochrome. And Yusuf was using the Astrodon LRGB and 5 nanometer hydrogen alpha O3 and silicone filters. And this was processed in Deep Sky Stacker, PixInsight, Photoshop, and Topaz Denoise AI. And this is also from Yusuf. This is the Bubble Nebula region. So that's a wide field view showing a whole host of nebulae. And in the next image here, Yusuf has actually labeled all of them for easier identification. So on the very left here, you can see the salt and pepper cluster in Cassiopeia. That's Messier 52. At the top, you can see the Northern Lagoon Nebula. You've got SH2-161, SH2-159, and of course the Bubble Nebula. Nova Cass is also visible down here. That was the Nova in Cassiopeia. We've got the Lobster Claw Nebula on the right. And there is a NGC 7510. That's a tiny little open cluster visible there as well. So that's a whole host of objects, very faint objects actually all in one picture. So it's a phenomenal job. And this was a total of 2 hours and 42 minutes of hydrogen alpha data, an hour and a half of O3 data, and total integration time was 4 hours and 12 minutes. And this is a close-up of the Bubble Nebula itself. And this is a zoomed-in view from the previous image. And again, this is the Bubble Nebula in Cassiopeia. And this is NGC 6914. This is a total of 1 hour and 42 minutes of hydrogen alpha data and an hour and 18 minutes of O3 data. So a total of integration time of 3 hours with the same Skywatcher Spirit 120 and the ASI 6200 camera. So again, amazing amount of nebulosity visible there, especially in the HA. So very nice result. Our next image is from Denis. This is the Bubble Nebula region. This was a total of 23-minute exposures taken with the William Optics GT71 at f4.7. And this is the Heart Nebula from Denis. This is also taken with the GT71 at f4.7. And this was a total of 61-minute exposures. And this was actually Denis' first attempt at the Heart Nebula. Our next shot here is from Mark Zaltzik. This is the Moon and Venus. And this is from June 11. And this was taken at 160 millimeters at ISO 400. And this is from Mark as well. This is the NLCs from June 25 or 26, and this was taken at 135 millimeter focal length. And this is the Sun in hydrogen alpha from Arnold Rivera. And you can see several large solar features there. A couple of those, I believe they're called prominences. And then this was the large sunspot region visible there. And you can see quite a bit of solar granulation as well on the surface. And this is from Arnold. This is the solar ISS transit. And Arnold submitted this image of the sun in calcium K line. And our next image is from Alan Hobbs. This is the Heart Nebula. And these are some of the images that Alan had shot at the Southern Saskatchewan Star Party and Grasslands National Park at the beginning of August 2020. And this shot and all the following ones were shot at 30 subs x times 1 minute. And this was with the RASA 8 and the ASI 2600 MC cameras with the Optlong L-enhanced filter. And this next one with the same equipment is the Eastern Veil Nebula from Alan. Very nice job. And this is the Pac-Man Nebula also from Alan. So a very nice shot and processing. The next shot is sent in by Josephine. This is the Perseid meteor shower. And you can see one of these meteorites streaking right to the left part of the frame. You can see the Milky Way going over the center and the Andromeda Galaxy right over there as well. And the next shot over here was from Arnold Rivera. This is a moon sweep over downtown Edmonton. And Alistair also submitted a time lapse here. I'll see if I'm able to play the time lapse. I believe I'm still sharing my screen, so hopefully that works. I hope everyone's able to see the time lapse here of the moon rising over downtown Edmonton. You can also hear the soothing sounds of the cop cars in the background. Nice. Okay, and the next shot here was actually a, oh, 1 second. Okay, sorry about that. Just have to quickly cycle through here. Okay, there we go. So this next shot was actually a collaboration between myself and Arnold Rivera. This is just from a few nights ago at the Northern Prairie Star Party. Although the sky was pretty cloudy most of the time, we did get maybe about an hour or two of clear sky time while we were there. So we decided to collaborate and get an image of the planet Jupiter. And you can see the great red spot right over here to the left. A couple of cloud bands and little festoons there. And that's the moon Io just off to the right of Jupiter. And we used Arnold's C11 and my QHY 462 planetary camera to get this shot. And we took about 2 minutes of video and then stacked it in Auto Stackert and then sharpened it slightly in Registax. And we also managed to get about 2 minutes of data on the planet Saturn. So you can see the Cassini division right here. You can see a couple of bands on the planet surface along with the polar hexagon there. And you can see the shadow being cast by Saturn onto the ring itself over there. And this last image is a reworked image of the Whirlpool galaxy. I took this data over the last, I guess, last 2 years or so. The older data was from my Fuji X-T2 mirrorless camera, which was the color data. And then I just added some monochrome data for luminance and hydrogen alpha from my ASI 1600. And this was with my 8-inch f3.9 reflector. And this was a total of about 9 hours of data between the two different cameras. And that is everything for this time. So thank you very much to everyone who submitted some images. For any of the images that I wasn't able to show this time, I've saved them for next time. So they will be in next month's Astro Imaging Corner. So thank you very much. And I hope to see some more images next time. Back to you, Tom.
Thank you, Abdur. That was really good. We really appreciate you putting it together. I've done 1 or 2 of those myself, and it does take a lot of work. So much appreciated by everybody.
It's always a pleasure.
So are there any announcements? Does anyone have any announcements? All right, well, I will say that if there are new members in attendance tonight, and I think I know we've got one for sure, please feel free to contact Murray Paulson for an orientation to the center. Murray's contact info is on the RASC website as the new member advisor. So that's been our program. Our next meeting is October the 18th, not the second Monday as usual, but we're delayed at a Monday because the second Monday is the Thanksgiving holiday. And I wish everybody clear skies. Thank you very much.